we'll look at numerical integration, which is given a integral, a definite integral. A definite integral has limits specified. So f of x is some nonlinear function, and we need to integrate that from lower limit a to upper limit b. Why is this useful? Well, not every time you can derive a indefinite solution to the indefinite integral. That is, f of x may not be integrable by hand analytically. Sometimes you can do tricks like substitutions to get the value for that integral, but many times it's not possible to find a closed form solution to f of x, in which case you cannot integrate that expression analytically. And so this chapter, this particular part of the course is about estimating that integral numerically. Another case where this could be useful is let's say that you're trying to figure out the data which comes to you doesn't even have a function. It's basically data points. So for example, if you're trying to estimate the power from an IC engine, so you have readings for the torque and the speed. And if you want to find the energy, which is the integral of power, torque times speed, then you need to use approximation to the integral in order to estimate that. So there are cases where you would need a technique which numerically finds the value of the integral. The key idea here is to approximate f of x with a polynomial. Okay, so what if f of x was a polynomial? Something like ax squared plus bx plus c. You know that we know how to compute the integral of a polynomial. It's very easy. We know the analytical formula. So we could use that in order to estimate the value of the integral. So approximate f of x with a polynomial and then integrate the polynomial. Okay, now we look at four methods to do this. Four methods. First one is known as a rectangular rule for integration. The second one is the trapezoidal rule. Okay, that will become very clear once I show you the expression for that. It basically approximates the function as with rectangles, which means that the polynomial involved is a constant. A trapezoidal will give you a linear polynomial. There's something called Simpson's 1/3 rule. Okay, so the 1/3 will be something which shows up in the function which we write, but that function is quadratic. And then the fourth one is called the Simpson's 3/8 rule, in which case you use a cubic polynomial. And there are higher order methods too, which we will not be looking at, but it's possible to have even better approximation using higher order methods. There's also something called adaptive integration. Basically, it switches between these two methods. So the function called quad in Octave, which basically switches between quadratic and cubic in order to get a better approximation to the integral. Okay, so we'll not get into those details, but we'll be good users of the function quad. Okay, so let's see what these rules do. So the first one is the rectangular rule. Okay, so what I have here is x. What I here have on the y-axis is f of x. And when I'm trying to compute the integral from, let's say the limit is a and b. It's essentially the area under this curve. That's the definition of the integral. So I equals a to b f of x dx equals to area under the curve f of x from a to b. So here's the first idea, which is decide number of segments you want to divide this interval in. Let's say there are n segments. 1, 2, 3, so on till n. Okay. Once you take the segments, then what you do is you know the value over here. It's f0. Okay, so we're going to essentially take that, then take the value at the next point, f1 and so on till fn minus 1. So we've basically found the values of f uh, at each of those points. Hold on, there's an error here. My bad. We fix this. Yeah, it's made an error on the first one. This should be the first one. This should be this is f0. This will be f1. This will be f2. So first grid point, second grid point, third grid point, nth grid point, n minus 1 n grid point. Okay, so now once we have that, what I would do is the following. I would assume that this will be my first area. This one will be my second one, and so on till I reach here. So I have this sort of a staircase-like structure, as you can see. And each staircase gives me an approximation to the area. So if I can find the heights of those rectangular blocks and sum them all over till B, then that would be the area. And of course, that's an approximation. So we can write let's call that I1 equals area. Okay, so the first rectangle, you can see that we have f0 is the height, and I should also put the width. The width is going to be, say that the width is delta x. I'll compute delta x in just a bit. So delta x is the width of each of those. So the first one is going to give me f0 times delta x. The second one will give me f1 times delta x. And I keep doing that till I reach n minus 1 times delta x. So I can pull the delta x out. So f0, f1, so on, fn minus 1 delta x. Okay, another way of doing the same approximation is as follows. We'll use the other figure. Okay, so let's draw f1 here. Let's ignore f0. Let's draw f1. This is f1. This is f2. F3, F2, F1, so on till we reach Fn. Okay, now I'm going to draw the rectangle slightly differently. So I'm going to draw this as my first rectangle, second one, third one, and so on till I reach the end. Okay, so now I have another approximation. Let's call that I2, the shaded area. That would be, we start from, as you can see, F1 and go all the way to Fn. So F1 plus F2, and I'm skipping that first step. It's essentially the same thing, except that now we'll have, we start from F1. Okay, so those are two approximations, and we can see the weaknesses of both approaches. If you look at the first approach, you'll see that there are areas we've missed. Like, for example, we've missed, this area is missed. That's not accounted for in our formula. This area is missed. And then this area is missed. So it sort of accumulates errors at every time step, every integration step. Here is a different problem. Here, instead of having the curve which is down, we are overestimating it. So we are including this area, which should not be part of the area under the curve, right? This is outside the yellow region. So what we'll observe is the following, that this one is actually going to give us a lower bound. It's not going to give, it's always going to be less than the actual area because of the way it is. Now, you could make it very fine and capture the subtleties in the curve, but usually you'll end up with some kind of error. It'll actually give you what I would call the lower bound. And then the other one, the problem is it's over approximate, so it'll give you an upper bound. Okay, so both of them have caveats. I low, an easy way of writing this would be Fi delta x, where I goes from 0 all the way to n minus 1. And I upper bound will be summation I goes from 1 to n Fi delta x. So the formulas are simple, but they will not give the true value. We also have to specify what delta x is. Here, delta x would be b minus a, the entire range, and we divide it into n slices. There are n grid points, so that would be delta x. Okay, so clearly one of the biggest issue with our approximation is that a straight constant for each of those, a constant approximation like this one doesn't capture the curve, especially if the curve is increasing, decreasing, and not a constant. So if it's a constant, fine, you're good, but not if the curve is something which is not constant. So we have to now, we'll say, how about we choose a straight line without a constant slope, sorry, a straight line with constant slope, but not a constant per se. So the next method, which is inspired from the limitations of you assuming a constant, is to use a straight line to approximate 2 points. So the next one is known as the trapezoidal rule. And it'll be obvious in just a bit why it's called trapezoidal rule. So here what we do is the following. We have, as usual, A and B. We'll split it into n intervals, each of length delta x doesn't change. But we'll do the following. Instead of trying to approximate this by a constant, we'll approximate the shape with a straight line. So these are 2 points, f0, f1. We'll basically fit a straight line. Okay, then we have again a straight line, and so on. Now, this curve happens to be sort of has a constant sort of slope the way I drew it, but it's not necessary to be a straight line, right? It could be quadratic, for example, in which case a straight line would. So it looks like I'm getting good approximation just because of the way I defined. But here, maybe when you do it over here, maybe you'll just get it. Yeah. So it looks good here, but in principle, there could be wiggles or it could be a shape which cannot be approximate straight line. Anyway, so if this is the case, then, and you are interested in computing this area, all you have to do now is compute the area of this particular shape. So the shape has got two parallel lines and two non-parallel or parallel lines. Other lines need not be parallel. So that is actually what the shape is called, a trapezoid. And that's why the name is trapezoidal rule. Trapezoid, and so on. Now the area of this curve can now be written as, so I need to sum all those orange regions which I have or will draw. It's going to be the area of a trapezoid is the width, which is delta x. So maybe there's a better way to write delta x times the average of the heights, right? So height is f0 and f1. Those are the two heights of the two lines of the trapezoid divided by 2 is average. And then second one will be delta x, f1 plus f2 delta x, and so on. Eventually, I'll get delta x fn minus 1 fn divided by 2. So I can pull the delta x out, and then you'll observe that you will get f0. So you can see f1 appears 2 times. F1 here, f1 there, and then f2 will appear 2 times, so on. So it will be twice f1 plus twice f2, and that keeps happening till I reach to fn minus 1, and then fn is only going to be a single one. This whole thing times delta x divided by 2. So I is a shorter way of writing this is to write like this: delta x divided by 2 summation. Well, let's pull the last two terms out. Plus, let's put a summation. So write twice summation. And this will go for, as you see, I will go from 1 all the way to n minus 1. Okay, that's the formula. Okay, and then the other thing is delta x is p minus a divided by n. Okay, let's just solve a problem which will illustrate this. And then I'll just choose something which is relatively simple. That way we can get an intuition. So here's the problem. Example 1. Compute I equals x squared dx from 0 to 1 using a rectangular rule, B, trapezoidal rule, and then C, um, analytical calculations. Okay. Okay. And then let's assume that we are told to use only six intervals. Okay, now this is something which is a tunable parameter. 6 means there are 6 grid points. This approximation gets better as you increase the grid points. You really don't want to do that calculation by hand. You probably want to use Octave to do it, but just focus on n equals 6. So what we have here is n is 6, a is 0, b is 1, upper and lower limits. So delta x is b minus a divided by n, which is 1 minus 0 divided by 6, which comes out to be 0.1667. Okay, so this is going to be used to discretize the grid. So A, B, which is 0, 1. What this is saying is that you will have 6, 1, 2, 3, 4, 5. So this will be 0.1667, 0.3333, 0.5, 0.6667, 0.8333 should be 0 and 1. Okay, so that's what it means. So you have divided this interval into 6 halves. So 1, 2, 3, 4, 5, 6. Okay, so what I suggest doing this over here is the easier way to do this is to remember formulas tell us that for rectangular rule, we need to evaluate the function f of I at the grid points. Same for trapezoidal rule. We need to evaluate the function at the grid points. So let's just do that. And that will become much easier to use, right? So what we'll have here would be, we'll have F0, F0, F1, F2, F3, F4, F5, F6, 0, 1, 2, 3, 4, 5, 6. So we'll have those values. This would be 1. Oh, and just map some of them. This will be 0.5. So the best way to do this is probably a table. So just create a table for this. So we have x 0, 0.1667, 0.33, 33.5, 0.6667, 0.8333. And then 1. Okay, then this is f of x. So just squared it. 0.0278, 0.1111, 0.25, 0.4444, 0.6944, and then 1. So if it's easier, let me just write F0, F1, F2, F3, F4, F5, F6. Okay, so here's the formula. So part A, I lower bound. The rectangular rule, we need to sum from 0 to n minus 1, n being 6, so 0 to 5. Fi dx. So F0 plus F1 plus F2 plus F3 plus F4 plus F5 times dx. Dx is given to us, it's 0.1667. And then F0s are straight from this table. If you do that math, it comes out to be 0.2546. Okay, so what's the answer? We'll come to that soon. So that's the lower bound. The upper bound would be I equals 0. Sorry, I equals 1 to 6. F of I delta x. This is the formula shown here. So I goes from 1 to n equals 6. F1, F2, F3, F4, F5, F6 times delta x. So that comes out to be 0.4213. Let's use the trapezoidal rule. We call that trap equals. Okay, so the formula was right here. It's delta x divided by 2, f0 plus fn, fn being 6, plus 2i summation from 1 to n minus 1, so 1 through 5. So delta x divided by 2, f0 plus fn, fn being 6, plus summation, sorry, 2 times summation. I will go from 1 all the way to 5, fi. So that would be delta x divided by 2, f0 plus f6 plus 2i's, f1, f2, f3, f4, f5. Okay, so that I'll just write it down from what I got. I got 0.3380. Okay, that is just use the values from the table. Everything is given here. And then C is the analytical expression. So if you do 0 to 1, x squared dx, x cubed divided by 3, upper limit is 1, lower limit is 0. So it's 1/3 minus 0. So 1/3 is 0.1. Sorry, 0.3333. This is the true value, right? 0.333. Yes, so this is what I got from the rectangular rule, a lower bound. And you can see it is actually underestimating the value. So actual value is 0.33, it's giving 0.242546. That's exactly what we expected. The upper bound is giving 0.4213. Okay, so that's clearly overestimating the value. The trapezoidal rule is giving 0.3380, which is actually slightly overestimating the value of 0.333, but it's actually kind of accurate to about 2 decimal places. Okay, so the reason why trapezoidal rule sort of fails in this case, well, there's no reason why it shouldn't fail, right? But the reason why it could fail is because if you look at this integral, it is x square. Right? This is, we are asked to compute x square. Okay, and what the trapezoidal rule does, it basically approximates the points with a straight line. So it assumes that the equation connecting the 2 points f0 and f1 and so on is something like ax plus b. Because it doesn't capture the second order, you'll see that there is an error, 0.3380. Okay, so actually we'll get to Simpson rule, which will actually be a third order, a quadratic approximation. That should actually work much better because it's going to capture the quadratic in the integral. Okay, before we do that, let's just write some code. This shouldn't be very hard to do because it is a very simple formula. So I will just write it myself. So we can, of course, take the same expression. And we're not plotting, so I won't use close all. Okay, so let's take the same expression as before and see if we can integrate it. So f x is this how you write it? Square c. Save it. Let me just save it on the desktop. I'm blanking on how to. Let me just get something here. Just trying blanking on the syntax. The syntax is okay. F equals at x. Okay. Okay, now it should work. No. So the syntax at x. Parse error. Oh, my bad. Should be at x. Okay. Square. Okay. Okay, 0. Okay, so that works. Okay, so that's that. The analytical one is at x raised to 3 divided by 3, I think. Right? So we could do part C easily. Part C, that would be I analytic equals, let's specify the upper and lower limit. A equals 1, A equals 0, B equals 1. So when we want to find the analytic expression, it's going to be int f at b minus int f at a. So int means integral. Okay, run this. Okay, 0.333, we know that's right. Let's do it part A. Let's call it lower. We'll write a function called rectangular lower. So the inputs to this should be probably f, should be a, should be b, and then we need to choose n. So let's just choose n to be 6. Pass that n. Okay, now we need to write this function. So let's take this. I think it should be function equals, okay, and then save it. Rectangular. Okay, so what we had decided was dx was b minus a divided by n. We need the formula. The formula is dx times. Okay, so we need to generate points, grid points. So x I equals a dx b. This will work. Okay, so I'm kind of sort of hazy today on the way I track code, sort of blanking. So this is the way I would check code. N equals 6. So does this really work? Let's put compute dx. It's right. And then does this work? Will it give us grid points? Well, it does work. So all I need to do now is do summation. Let's compute that. F Fi equals f xi. You can check this too. F xi. Okay, there is a problem here. The problem is because the way I wrote this function, I assumed that x is a scalar, and so it will work. The moment you have pass x as a vector, x square will not work. So the change you need to make is that this is basically does element-wise multiplication. So let's redefine f. Okay, and then let's go here and then see if that works. So, okay, and now f xi. Okay, so it worked now. So you can check these values, exactly the values I have in the table. Okay, now that I've got x, now we just use the formula. The formula being when I did this for the rectangular rule, it was basically summation from 0 to n minus 1. So I need to go all the way till n minus 1. So let's just do this. So it'll be f sum f I 1, no, fi 1 through n minus 1. That'll work. Okay, I can check this. Fi 1 to n minus 1. It's not defined here. So fi to n minus 1. Okay, so it is actually taking. Okay, so it is actually taking the values from 1, 2, 3, 4, 5. So this will work fine. Okay, so let's run this. Okay, that doesn't look right. It's 0.1389. I think we got 0.325, I think. What's wrong? Okay, can somebody tell me what I might be doing wrong? 7, 2, 3, 4. The length fi a equals 0, 1, 6. Dx. Let's debug the issue here. So, wait, dx not defined. See. Okay, dx is fine now. F of fi is f of xi. Okay. Okay, so when I sum this, I need to sum 0 all the way to this value. So when I was doing f n minus 1, wait, what? Okay, fi n minus 1, my bad. Okay, so here's the problem. I was only going up to 0.444. This is incorrect. So it actually should be n minus 1. I think that'll work. So 0.2456. So it basically goes all the way from first one to the one but last one. Okay, so then if I want to do the same thing for upper bound, here I would write the code for upper bound. Upper, let's call that upper. And then I know for a fact that it's the same formula, except, well, it's the same form for the formula, but I need to go from the second one all the way to the end element. So it's saved. Let's go here. Okay, let's hope it runs now. Okay, so, well, it's printing this. Let me just suppress this output and then suppress, save. Okay, so, well, it's also, I didn't want it to print all this. Save. Save, okay. Okay, so here we are. We have analytical 0.333, 0.2546, exactly what we got, and 0.4213 for the overbound. Now, here's the thing about writing this code is that we can actually see how this, if at all, this improves. So let's just increase the grid point from 6 to, let's make it, I guess, 12. Okay, double it. So you see it's coming close to 0.33. Still, it's an upper lower bound. Let's go 24. Kind of close, but still not there. Let's go, I guess let's try 100. Quite close. And then we can go 1,000. Yeah, that's about there. It's like you can see that it takes so many, it took 1,000, n equals 1,000 to get about 2 decimal place accuracy. It's not a very accurate method.